Okay, now I just realized that I've been writing seconds for my units, but my unit of time is really the pendulum cycle. So you kind of want to think I should be writing pendulum cycle squared here and pendulum degrees per pendulum cycle, the 250 pendulum cycles. Let's just pretend the pendulum cycle is a second. It really wasn't, but we can correct that later. Okay, so as I stated just before I got cut off, because what happened was the memory card got full and got cut off. I was being careless about that. This function, the function that gives you omega in whatever units, should be the derivative of this function in whatever units. Now, if the units aren't the same, like this is in degrees and your angles in radians here, it's not going to look like it's the same. The slope of this graph is negative 0.4 when you measure theta in degrees. Okay? If theta was measured in radians, it would be somewhat different. So let's see what the comparison would be. Now, I wrote this down and actually completed the explanation, so I'll just have the point. So this is your your d theta dt. Okay, if t is in pendulum cycles, then d theta dt will be in radians per pendulum cycle. And that would be the formula or the equation for the d theta dt, or your omega function, if you were measuring your angle in radians. Okay? Degrees, well, it takes, a radian is 180 over pi degrees, because a 360 degree rotation is a 2 pi radian rotation. Okay? So 2 pi radians is 360 degrees, so that pi radians would be half of 2 pi radians would be half of 360 degrees, 180 degrees. So if you want to go from degrees per second to radians per second, you have to multiply by 180 over pi, which is about 60. It's 57.1 or 57.3, I don't remember, because I never used the conversion. But that's pretty close to 60. So I'm going to say that omega in radians per second should be 180 over pi times, omega, should be 180 over pi times, didn't say that right. Omega in degrees per second should be 180 over pi times omega in radians per second. Why? Because a degree is 180 over pi, a radian is 180 over pi degrees. Make sure you understand that. It's getting a little late here. So basically then we multiply 60 times our omega, the omega that we got here, so I'm going to put that in yellow. This is omega in degrees per second. Well, if you multiply this by 60, this comes out 0.384, if I got that right. And this comes out 60. So you get negative 0.38t plus 60. I'm not going to worry about the 4 because I'm doing all kinds of inaccurate fudging here. But not really fudging, just, not doing the calculations that accurately. So the negative 0.38t plus 60. Well, what's that mean? That means that omega in degrees per second, to be consistent with this theta function that we got from all the simultaneous equations and everything, should have a slope of negative 0.38, shouldn't it? And what's our slope over here? Do you remember? Negative 0.4. That's closer than I expected to get, but I'm not too surprised. I expected to get reasonably close. Okay? Now, the 60 doesn't match up with the y-intercept or the omega-intercept of that graph. But your assignment is going to be to just run through all this with your own data. And if you didn't have data, for example, if you're the person timing, you wouldn't have written down data. If you're running the timer, you can just use this data. But do it accurately, not the way I did it, and see just how close it comes out. It should come out quite close. And And of course, this all depends on how well you draw that curve for the theta graph and how well you fit that straight line, because there's some leeway in how you fit that. So you're not gonna nail it, but let's just see how close you get, and I think you'll be surprised.